We need to talk about what happened on November 5th, or perhaps more accurately, what did not happen. For months, the astronomical community and a growing number of us watching from the sidelines had been waiting. We had predictions, we had calculations, we had a clear expectation of what our interstellar visitor, 3I Atlas, would look like after it completed its fiery passage around the Sun. Then, on November 5th, the first images arrived, and they showed something that simply should not be possible, a reality that directly contradicts what the laws of physics tell us must be true if this object is a natural comet. Before we dive into the deep, unsettling waters of this mystery, I need you to do something for me. Please take a moment to hit that like button, and if you haven't already, subscribe to this channel. We're on the front lines, tracking what is arguably the most significant celestial event in human history, and you will want to be here for every single development as it unfolds. And speaking of unfolding events, tell me in the comments where you are listening from right now, and what time it is in your part of the world. I want to pose a question directly to you, a question that sits at the very heart of this entire investigation. Do you believe the missing tail is definitive proof of artificial propulsion, or is there a subtle, yet unknown natural explanation that we have simply not considered yet? The images that sparked this intense debate came from credible professional sources. The Arnaves Observatory in Spain captured 3I Atlas on that crucial day. The Virtual Telescope project did the same, providing another independent set of eyes on the object. I want to be perfectly clear about this. These are not amateur setups in someone's backyard. These are sophisticated, well-equipped facilities with decades of collective experience in the specific, challenging art of photographing comets. They know precisely what they are looking at, and they know what a comet should look like after rounding the Sun. What their powerful instruments captured was a compact fuzzy ball of light. It had a coma, that familiar halo of gas and dust that surrounds a comet's nucleus. But it was missing the one feature that should have been the most prominent. There was no clear cometary tail. None. The object's overall shape, its morphology, was essentially unchanged from the photograph the Hubble Space Telescope took back in July. This was before perihelion, before the intense solar heating, before the period of extreme activity that was supposed to transform this object into a spectacular display of cosmic outgassing. Let me be absolutely clear about why this is so profoundly important. This isn't about being disappointed by a less than spectacular visual show. This is not about aesthetics or missing out on a pretty picture for our space calendars. This is about fundamental physics. This is about what the laws of momentum conservation demand must happen when an object accelerates in a way that gravity alone cannot explain. And make no mistake, 3I Atlas did accelerate. NASA's own Jet Propulsion Laboratory, the JPL, confirmed it. The data is not hidden. It is public, available for any scientist to download and analyze. The non-gravitational acceleration was measured, and the signal is robust, standing at a statistical significance of 3.7 standard deviations. In the world of science, that is not random noise or a measurement error. That is a real, undeniable signal. The acceleration has two distinct components. A radial push directly away from the Sun, measured at 1.1 times 10 to the power of -6 astronomical units per day squared, and a transverse component, a push perpendicular to the Sun's direction, at 3.7 times 10 to the power of -7 astronomical units per day squared. These numbers might sound abstract and technical, so let me translate them into what they actually mean. This acceleration, if it was caused by the natural rocket effect of gas jetting off the surface of a comet, means that 3I Atlas had to lose more than 13% of its total mass during its passage around the Sun. Let that number sink in for a moment. 13%. That is not a thin layer of frost gently evaporating into space. That is a substantial, massive chunk of the object's entire bulk being violently expelled. The renowned astrophysicist Avi Loeb calculated this using the straightforward, time-tested principles of momentum conservation. The formula is not complex. It states that the fraction of mass lost is equal to the time of the perihelion passage multiplied by the measured acceleration, all divided by the speed at which the gas is ejected. The perihelion passage time, the period of most intense heating, was approximately 1 month. The acceleration is the value we just discussed, confirmed by JPL. And the ejection speed for a natural comet, at the surface temperature 3I Atlas would have experienced, is around 300 meters per second. This is the thermal speed of molecules sublimating, turning from solid ice directly into gas, heated by the relentless glare of the sun. When you plug those numbers into the equation, the result is inescapable: a minimum of 13% mass loss. That is the floor, not the ceiling. The actual value could be even higher. Now, I want you to truly think about what 13% mass loss means in practical physical terms. If we assume 3I Atlas has a nucleus roughly 5 kilometers in diameter, which is consistent with the observational data we have, and it lost 13% of its mass, we're talking about at least 5.12 billion tons of material being ejected into space. That is billion, with a B. That is a mountain of ice and dust, vaporized and thrown into the void. That much ejected material does not simply vanish without a trace. It forms a cloud, an enormous dense coma of dust and gas that is then relentlessly pushed by two forces from the sun: solar radiation pressure and the solar wind. That cloud should be obvious. It should be enormous. It should have formed a tail, a classic textbook cometary tail streaming away from the sun, a feature that should have been easily visible in any half-decent telescope image taken from Earth. And yet, there was nothing. The November 5th images show a coma, yes, but it is not significantly different from what we saw back in July. The object's overall shape has not changed dramatically. There is no massive, brilliant tail. There is no visual evidence of the kind of cataclysmic outgassing event that would be required to produce the observed acceleration through natural cometary processes. This is the central contradiction we are now forced to confront. Let me put this in an even sharper perspective by showing you what we should have been seeing. On November 3rd, just 2 days before 3I Atlas was photographed, the very same Unresponsive observatory in Spain also took an image of Comet Lemon, a regular run-of-the-mill comet from our own solar system. Comet Lemon displays a clear, obvious, textbook-perfect cometary tail, pointing directly away from the sun. This is what comets do. This is what they are supposed to look like when they are actively outgassing and interacting with the sun. Comet Lemon is not special. It is not extraordinary. It is simply behaving like a comet, doing what comets have done for billions of years. But 3I Atlas, according to the acceleration data from JPL, should have been outgassing far more violently than Comet Lemon during its perihelion passage. It should have lost over 13% of its mass. It should be surrounded by a cloud of ejected material orders of magnitude more massive than whatever Comet Lemon is producing. And yet, the images show less cometary activity, not more. This is the paradoxical question that now hangs over this entire investigation. How does an object accelerate more but appear to outgas less? The physics demands one thing, but the visual evidence shows the complete opposite. Both cannot be true if 3I Atlas is a natural comet. Something is fundamentally wrong with our understanding of this object. Now, some of you might be thinking, maybe the gas is there, but we just cannot see it. Perhaps it is too diffuse, too spread out, or too faint for our telescopes to detect. But that counter-argument simply does not hold up to scrutiny. The sheer amount of mass required by the acceleration, billions of tons, is so large that the resulting cloud would be detectable. We have precedents for this. We successfully detected the much, much smaller plume of carbon dioxide around 3I Atlas back in August. That detection was made by the SphereX instrument and the James Webb Space Telescope when the object was much further from the Sun and therefore far less active. If we could see that small amount of gas from that great distance, it is almost certain we would see a cloud containing billions of tons of freshly ejected material now, after its closest and hottest approach to the Sun. In this case, the absence of evidence truly is evidence of absence. The tail that physics demands should be there is simply not. To make this timeline even clearer, let's walk through the sequence of events. Between July and September of this year, 3I Atlas was observed continuously and extensively. We have a staggering 4,022 data points from 227 different observatories around the world. During that entire period, the object showed absolutely no detectable non-gravitational acceleration. Zero. Its motion was entirely consistent, with a trajectory determined by gravity alone, like an inert rock coasting through space. Then came October. As 3I Atlas approached its perihelion, its closest point to the Sun, everything changed. Suddenly, the acceleration appeared. the object began to deviate from its predicted purely gravitational path. The Atacama Large Millimeter Array, or ALMA, one of the most powerful radio telescope arrays on the planet, detected that 3I Atlas was 4 arc-seconds away from where it should have been. 4 arc-seconds that gravity alone could not explain. This tells us that whatever caused the acceleration happened at Perihelion on October 29th, or very close to it. On the surface, this timing seems to fit the natural comet model perfectly. Perihelion is when solar heating peaks, when surface ices would sublimate most violently, and when outgassing would be at its absolute maximum. So the timing of the cause fits the natural explanation. The problem is that the aftermath does not. If the acceleration was caused by a massive outgassing event at Perihelion, then the gas from that event should still be visible now, just days later. Gas does not just disappear into the vacuum of space. It spreads out, it forms a cloud, and it gets pushed by radiation pressure into a tail. We should see the remnants of that explosion of activity. We do not. The tail that never came is not just a curiosity. It is a direct challenge to the natural comet hypothesis, a piece of evidence that points towards something far stranger. This brings us to the uncomfortable question that Avi Loeb has been raising with unwavering consistency. If the acceleration was not caused by cometary outgassing, what caused it? The options are severely limited. You can accelerate an object in space through the force of gravity, but we have already accounted for all known gravitational influences, and they do not explain the observed deviation. You can accelerate an object through the rocket effect of expelled gas, but that requires the massive visible gas cloud that we are not seeing. Or you can accelerate an object through some other propulsion mechanism, an engine technology, something that can produce thrust without requiring the violent expulsion of 13% of the object's mass through natural sublimation. This is the hypothesis that makes many people uncomfortable, and I understand why. The history of astronomy is filled with supposedly anomalous observations that, upon closer inspection, turned out to have perfectly mundane explanations. Jumping straight to aliens is generally not the smartest bet, but this is different. We are not starting with the assumption of artificial propulsion and working backward to fit the evidence. We are starting with the observations, with the hard data, with measurements that do not fit the natural explanation. The acceleration is real. The missing gas cloud is real. These are facts, not speculation. The artificial propulsion hypothesis is not the starting point of this investigation. It is where the data is relentlessly pushing us as the natural explanations continue to fail to account for what we are seeing with our own eyes. Let me be very precise about what we are and are not claiming. We are not saying that 3I Atlas is definitively an artificial object. We are saying that the post-perihelion observations are fundamentally inconsistent with the natural comet hypothesis, given the measured acceleration. That is a scientific statement. It is testable. It makes predictions. If 3I Atlas is a natural comet that accelerated through outgassing, then there must be a massive gas cloud around it, and we should be able to detect that cloud in upcoming, more detailed observations. This is why the November 5th images matter so much. They are our very first look at the object after it passed through the solar furnace. They are the first test of the predictions made based on the acceleration data, and they are not showing what the natural comet model predicts. Not even close. The tail should be there. The massive coma should be obvious. The evidence of a 13% mass loss should be unmistakable. Instead, we see an object that looks remarkably, unnervingly similar to how it looked before perihelion, before the supposed massive outgassing event ever took place. Think about the sequence of events here one more time. 3I Atlas coasted through space for millions, perhaps billions of years. It entered our solar system. For months, it showed no acceleration, behaving exactly like an inert object following a purely gravitational trajectory. Then, it approached the Sun, passed perihelion on October 29th, and suddenly accelerated. The acceleration was measured, the math was done, and physics tells us this requires a colossal loss of mass. But the images taken just a week later show no evidence that this mass loss ever occurred. That sequence of events simply does not make sense if this is a normal comet. The comparison with Comet Lemon really drives this home. Lemon is out there, doing normal comet things, making a nice visible tail, looking exactly like we expect a comet to look. 3I Atlas, which should be far more active based on its acceleration data, looks less active than Lemon. How does that work? How do you accelerate more but outgas less? The most straightforward answer is that you use a propulsion method that does not require massive outgassing. You eject material at a much higher velocity, so you need less of it to produce the same thrust. But now we are back to talking about technology, about artificial systems, about the very hypothesis that makes people so uneasy. We have more critical observations coming. The JWST spacecraft is observing 3I Atlas right now, from a unique vantage point impossible from Earth. On December 19th, 3I Atlas will make its closest approach to our planet, a mere 269 million kilometers away. That is when Hubble and the James Webb Space Telescope will have their best opportunity for detailed spectroscopy, to measure the exact composition and density of any gas cloud surrounding the object. Those December observations are going to be definitive. If there is a massive gas cloud, Webb will detect it. And if it is not there, if the December observations confirm what the November 5th images are suggesting, then the natural comet explanation is not just weak, it is ruled out by the data. The tail that never came is not just a missing feature, it is a signpost pointing towards something we have never encountered before, and in just a few weeks we're going to find out just how deep this mystery truly goes. While the astronomical community was grappling with the physics of those baffling November 5th images, something completely unprecedented was happening in Washington, D.C. Representative Anna Paulina Luna from Florida's 13th District did something that rarely occurs at the intersection of politics and pure space science. She went public with her growing frustration over what she described as NASA's refusal to release critical data about 3I Atlas. This was not a request for just any data, but for specific high-resolution images that could answer fundamental questions about what this object actually is. On November 4th, Representative Luna submitted her second official letter to NASA regarding 3I Atlas. Her first letter, sent all the way back on July 31st, had proposed something incredibly ambitious, redirecting the Juno spacecraft from its long-term orbit around Jupiter to intercept 3I Atlas. The proposal was detailed, suggesting that a specific engine burn on September 14th could position Juno for a close encounter within 53 million kilometers in March of 2026. The estimated cost for this historic mission extension was a mere $15 million. But by November, Luna's tone had shifted dramatically, from optimistic collaboration to formal demand. The second letter was not about planning future missions. It was about data that NASA already possessed, but was refusing to share with the scientific community and the American public. The request was remarkably precise. Luna demanded the highest resolution images from the HiRISE camera, which is on board the Mars Reconnaissance Orbiter, taken on October 2nd and 3rd. These images were expected to have a resolution of 30 kilometers per pixel. She also requested any supplementary data from other Mars missions that might have detected unusual activity when 3I Atlas passed within just 30 million kilometers of Mars around that same time. Finally, she asked for all relevant observations from the Parker Solar Probe, Hubble, and the James Webb Space Telescope. These are not vague fishing expedition requests. These are specific instruments, specific dates, and specific datasets that should exist if these missions were operating as planned. The timing of this shift in Luna's approach, from her first letter to her second, tells you everything you need to know about what was likely happening behind the scenes. In July, she seemed optimistic about a collaborative effort to study this object. By November, it appears she had concluded that NASA had been observing 3I Atlas extensively, but was withholding the most crucial findings. That is not just speculation, it is the clear implication of her letter. NASA has the data, NASA is not releasing it, and now a member of Congress is formally demanding to know why. Avi Loeb, in his relentless pursuit of transparency, sent his own request directly to Professor Alfred McEwen at the University of Arizona, the principal investigator for the HiRISE camera team. As of the publication of his latest article on the subject, he had received no response. Think about that for a moment. The lead scientist on arguably the highest resolution camera that photographed 3I Atlas during its pivotal Mars flyby is not responding to inquiries from one of the most prominent astrophysicists in the world. This silence is deafening. The HiRISE images are scientifically crucial. With a potential resolution of 30 kilometers per pixel, they would be approximately 3 times sharper than Hubble's best public image from July 21st. For an object whose size is still uncertain, whose surface properties are a complete mystery, and whose composition is hotly debated, that level of resolution could be transformative. The brightest pixel in the HiRISE images would provide the best constraint yet on the actual physical size of the nucleus. We could finally determine if 3I Atlas is truly the 5-kilometer diameter solid object that some estimates suggest, or if it is something else entirely. We could look for surface features, for active jets, for any asymmetries that might help explain its bizarre acceleration. But we cannot do any of that without access to the images. The controversy exploded into the mainstream consciousness in a way that no one could have predicted. Kim Kardashian tweeted at NASA Administrator Shah Duffy, asking for clarification about 3I Atlas. Her tweet was simple, direct, and reached her hundreds of millions of followers. Duffy's response was reassuring in tone but was notably evasive in its content. He acknowledged it was a great question, and stated that NASA's observation showed it was the third interstellar comet to pass through our solar system, but he offered no new data and did not address the specific anomalies that were causing so much debate. Representative Luna's involvement represents something much deeper than just one congressperson being curious about space. Luna sits on committees with direct oversight authority over agencies like NASA. Her questions are not casual inquiries. They are formal congressional actions. When a member of Congress demands that a federal agency release data that was collected with taxpayer dollars, it creates a level of pressure that simply did not exist before. NASA can ignore emails from scientists, but it cannot as easily ignore formal inquiries from Congress, especially when those inquiries become public and generate significant media attention. The government shutdown that began in October complicated everything. NASA's official website stopped updating. The usual channels for data release went dormant. The Public Affairs Office that would normally handle media inquiries was shut down. This created a perfect storm of opacity, an information vacuum, right at the moment when 3I Atlas was passing through its most scientifically interesting and critical phase. Was the timing of the shutdown simply unfortunate, or was it convenient? That is a question beyond the scope of this investigation, but the effect was undeniable. It prevented the normal flow of information that usually accompanies major astronomical events. Despite the official shutdown, some raw data continued to flow through automated systems. This is how we got those intriguing, though low-resolution, images from the Perseverance rover on Mars from October 1st and 3rd, which might show 3I Atlas as a faint smudge in the Martian sky. Astrophotographer Simeon Schmaus painstakingly stacked 20 images from the rover's Mastcam Z camera and found a faint object in the constellation Corona Borealis, very close to where 3I Atlas was predicted to be. Is it definitive proof? No. But it is highly suggestive. However, these are raw, unprocessed images from a camera designed to photograph rocks on the Martian surface, not distant comets. The high-resolution, high-rise images, purpose-built for exactly this kind of observation, remain locked away. The frustration within the scientific community is palpable. Multiple Mars orbiters had 3I Atlas in their sights during the October 3rd close approach. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter did photograph the object, and they did release some images. They show fuzzy dots, 3I Atlas against a field of stars. But these images are from cameras designed to image the Martian surface at close range, not objects tens of millions of kilometers away. Their scientific value, while real, is limited. NASA's Mars Reconnaissance Orbiter, on the other hand, possesses the HiRISE camera, an instrument built for exactly the kind of long-range, high-resolution imaging that could reveal crucial details about 3I Atlas. We know those images exist. They were taken on October 2nd and 3rd when 3I Atlas was just 30 million kilometers from Mars, and they are not being released. Why would NASA withhold scientific data about such a significant astronomical object? There are several possible explanations, and not all of them involve a conspiracy or a cover-up. One benign possibility is that the images require extensive calibration and processing before they can be released, and the government shutdown simply interrupted that process. Another possibility is that the images show something unexpected, something that requires careful analysis and context before being released to the public to avoid misinterpretation. Scientists generally prefer to understand their data before publishing it, especially when that data might generate significant public interest or misunderstanding. A third possibility, the one that generates the most speculation, is that the images show something NASA does not want to discuss yet. This doesn't necessarily mean aliens or technology, but perhaps something that contradicts previous public statements or reveals a level of uncertainty where certainty was previously claimed. Bureaucracies do not like admitting they were wrong, and they especially do not like admitting uncertainty when they have previously projected confidence. This entire controversy highlights a fundamental tension in how space agencies operate. NASA is both a scientific organization and a government bureaucracy, and those two identities do not always align. Science demands transparency, immediate data release, and open debate. Bureaucracy demands careful messaging, controlled narratives, and avoiding statements that might later need correction. When an object like 3I Atlas comes along, something genuinely anomalous and unexplained, that tension becomes acute. Representative Luna's demand for transparency is essentially a demand that NASA prioritize its scientific identity over its bureaucratic one, at least in this case. Release the data. Let the scientific community analyze it. Let independent researchers contribute their expertise. The Mars Reconnaissance Orbiter cost $720 million to build and launch. Every dollar of that came from taxpayers. The HiRISE camera, one of the most sophisticated imaging systems ever sent to another planet, exists because the public funded it. When that camera photographs something as significant as 3I Atlas, the resulting images are not NASA's private property to withhold. They are public data, collected with public resources, and the public has a right to see them. As we wait for the HiRISE images, as we watch this bureaucratic standoff play out, 3I Atlas continues its journey through our inner solar system. It does not care about governmental politics or agency rivalries. It is simply moving, following its trajectory, either expelling gas in a way we have not detected, or using some other method to adjust its course. The very images that could help us understand which of those is true exist in a database somewhere, ready to reveal their secrets, and we cannot see them. Not because they do not exist, but because the people who control access to them have decided, for whatever reason, that now is not the time to share. There is something deeply, fundamentally wrong with the chemistry of 3I Atlas. This anomaly has nothing to do with the missing tail or the mysterious acceleration. This is about the specific metals detected in the gas cloud surrounding the object. It is about what was found, and more importantly, what was conspicuously absent. When the Very Large Telescope, or VLT, in Chile aimed its powerful spectrographs at 3I Atlas back in August, it detected the clear signature of nickel in the Coma. On its own, this is not shocking. Comets are known to contain metals, remnants of the primordial cloud from which their star system formed. But the VLT spectrum showed something that should not happen in nature. It showed nickel without a corresponding amount of iron. Let me explain precisely why this is so significant. Nickel and iron are what astrophysicists call siderophile elements, meaning they are metal lovers that preferentially bond with other metals rather than with oxygen or silicon. They are forged together in the fiery cores of massive stars and are scattered together across the cosmos when those stars explode as supernovae. The ratio of iron to nickel throughout the universe is remarkably consistent, at roughly 20:1. For every single nickel atom you find, there should be about 20 iron atoms nearby. This is not a loose correlation. It is one of the most stable and predictable elemental ratios in all of astrophysics. We find it in meteorites that fall to Earth, in asteroids throughout our solar system, in the Sun, and in other stars. Everywhere we look in the natural universe, iron and nickel travel together in these predictable proportions, except, it seems, in 3I Atlas. The spectra from the VLT show clear, strong emission lines for nickel, but the iron lines that should be right there alongside them, that must accompany them in any known natural object, are either completely absent or are far, far weaker than they should be. The nickel-to-iron ratio in 3I Atlas is orders of magnitude higher than in any known natural object, including the previous interstellar comet, 2II Borisov, which displayed a perfectly normal ratio. Now, here is where this observation takes a turn towards the extraordinary. On Earth, when we produce nickel for industrial purposes, we often create nickel-rich alloys that have been deliberately processed to separate the nickel from the iron. But there is a specific industrial method for refining nickel to extremely high levels of purity called the MOND process. This process uses a fascinating molecule called nickel tetracarbonyl, which consists of one nickel atom bonded to 4 carbon monoxide molecules. This compound is highly volatile, meaning it evaporates easily at low temperatures, and it is the key to creating pure nickel. The team of researchers analysing the VLT data made a remarkable suggestion. They proposed that the nickel emission they were seeing from 3I Atlas could be perfectly explained by the presence of nickel tetracarbonyl in the Coma. This molecule breaks apart very easily when exposed to the sun's ultraviolet light, releasing individual nickel atoms and carbon monoxide. This would explain why we see nickel, and it would also explain why we do not see iron, because iron does not form similar volatile carbonyl compounds under the conditions found in comets. Nickel tetracarbonyl is an industrial compound, a product of deliberate chemical engineering. It is not something known to form naturally in the cold, low-pressure environment of a comet's surface. Before we jump to any conclusions, I want to be fair to the researchers. They did not claim that 3I Atlas is artificial. They suggested that perhaps, under some exotic conditions that we do not yet understand, nickel tetracarbonyl could form naturally in interstellar space or in unusual protoplanetary disks. That is a possibility, certainly, but we need to be honest about what we are proposing here. We are suggesting that an industrial chemical, one that requires specific and controlled conditions to synthesize on Earth, somehow formed naturally on an object that then travelled through interstellar space for millions of years. It is a hypothesis that requires us to invent new, unobserved astrophysical mechanisms. The alternative hypothesis is uncomfortable, but it is also straightforward. If 3I Atlas were a manufactured object, a technological artifact of some kind, using nickel-rich alloys in its construction would make perfect engineering sense. Nickel is stronger than iron in many applications. It is more resistant to corrosion, and it is better at handling extreme temperatures. For a probe or a vessel designed to survive for millions of years in the radiation-soaked vacuum of interstellar space, nickel alloys would be an excellent choice for construction. If that object were venting material, either as a form of propellant or through the slow degradation of its surface, you would expect to see nickel in the emissions, without necessarily seeing iron, because the original construction simply did not use iron-based materials. The nickel-to-cyanide ratio adds another perplexing layer to this chemical puzzle. Comets are naturally rich in cyanide compounds, which form in the cold environments where comets are born. The previous interstellar visitor, Tui Borisov, showed typical cyanide abundances, exactly what you would expect from a natural icy body. 3I Atlas, by contrast, shows a nickel-to-cyanide ratio that is orders of magnitude higher than any known comet. There is simply far more nickel relative to the cyanide than there should be. Let me be very clear about the statistical significance of this. When Avi Loeb compiled his list of the anomalies of 3I Atlas, he calculated the likelihood of each one occurring naturally. For the nickel-to-cyanide ratio, he determined that the probability of this occurring in a natural comet is less than 1%. This is not a guess. It is based on a direct comparison of 3I Atlas to the entire population of known comets. The nickel chemistry of 3I Atlas is a greater than 3 sigma outlier. It is not impossible for natural objects to be outliers, but when you begin to stack multiple 3 sigma anomalies on top of each other, you start to run out of probabilistic room very quickly. The overall composition of the Coma only deepens the mystery. Data from the James Webb Space Telescope's spectroscopy showed that the Coma of 3I Atlas is overwhelmingly composed of carbon dioxide, at 87%. It has 9% carbon monoxide and only 4% water. For comparison, most comets in our solar system are dominated by water ice. The dominance of carbon dioxide in 3I Atlas suggests it formed in an extremely cold environment, far from its host star. But here is the puzzle. If it formed in an ultra-cold environment, where did the metals like nickel come from? Metals require hot environments to form and process. So we have evidence of formation in a very cold place and evidence of processing in a very hot place, 2 conditions that seem to be mutually exclusive. The geophysicist Stephen Burns, who's been tracking 3I Atlas closely, offered another perspective. He looked at the post-perihelion images, saw the missing tail, noted the acceleration, and concluded that 3I Atlas is likely not a fragile pile of ice and dust. but a fairly solid chunk of metal and carbon. If the object is primarily metallic with a carbon-rich coating, that would explain the nickel emissions, the lack of a massive tail, and its incredible resilience to the sun's heat. A solid metal object would not react violently at perihelion the way a normal comet would. But if it is a solid metal and carbon body, where did it come from? Natural processes do not create such objects in isolation. Every single natural explanation for the strange chemistry of 3I Atlas requires us to add special conditions, to invoke unusual environments, or to propose exotic, unobserved processes. Each explanation leaves critical questions unanswered. This does not prove that the object is artificial, but it does mean that we cannot simply assume it is natural and call it a day. The chemistry demands an explanation, and the explanations we currently have are either incomplete or require us to believe in phenomena we have never actually observed. The nickel without iron is not just an anomaly. It is a signpost, pointing towards something we do not understand, something that does not fit into our neat models of how the cosmos is supposed to work. In the days leading up to its closest approach to the Sun, something truly remarkable happened that has not received nearly enough attention. The Sun launched a massive coronal mass ejection, a CME, aimed directly at 3I Atlas. This was not a glancing blow or a near miss. The geophysicist Stephen Burns tracked the event in real time, and his forecasts leading up to it were uncannily accurate. A massive halo CME erupted from the far side of the Sun on October 21st, aimed precisely at the location where 3I Atlas would be during its perihelion passage. The timing was almost surgical, with the impact predicted for around October 25th, just 4 days before perihelion. Burns had been predicting this for months. Not this specific CME, but the high likelihood that solar activity would spike during 3I Atlas's closest approach. His reasoning was based on how large, massive objects can affect the electrodynamics of the inner solar system. The Sun is not just a ball of hot gas, it is a complex electromagnetic environment, and a massive object like 3I Atlas, with its substantial coma, represented a significant disturbance to that environment. Burns predicted the Sun would react, and it did, exactly as he forecasted. Now, let's talk about what a CME does to a normal comet. Coronal mass ejections are not gentle events. A CME is a billion-ton wave of superheated plasma and tangled magnetic fields, travelling through space at incredible speeds. When this wave of energy and matter hits a comet, several things are expected to happen simultaneously. The plasma interacts with the gas in the coma, causing it to glow brightly. The immense pressure of the plasma wind, orders of magnitude stronger than the normal solar wind, pushes harder on any gas and dust, often triggering dramatic brightening of the tail, and even causing it to tear away. For a comet that is already actively outgassing, a CME impact is like throwing gasoline on a fire. The additional energy should trigger even more sublimation, creating a visible outburst. Some comets even fragment under this incredible stress, unable to hold themselves together. The famous comet Eson, for example, disintegrated during its perihelion in 2013, shredded by the combination of solar tides and CME impacts. If 3I Atlas is a loosely bound rubble pile of ice and rock, as most comets are thought to be, the CME should have done significant visible damage. But here is what actually happened. Nothing. Or, more precisely, nothing that we can detect from the available observations. 3I Atlas did brighten by a factor of 5 between early October and early November, but that brightening is entirely consistent with the normal heating it experienced as it approached the Sun. It does not require a CME impact to explain it. There was no dramatic outburst, no sudden spike in brightness corresponding to October 25th, when the CME should have arrived. There was no sudden tail formation triggered by the plasma pressure. The object passed through perihelion, was presumably slammed by a massive CME, and emerged from the other side looking essentially unchanged. This is deeply bizarre. CMEs are incredibly energetic events. When the energy is dumped into a comet's coma, it has to go somewhere. It should excite atoms, ionize molecules, and create visible light. We should have seen those effects. Yet, the data from the satellites that monitor the Sun continuously show a brightness increase consistent only with distance-based heating, not with a CME-induced explosion of activity. There are a few possible explanations for this non-event. One is that the CME simply missed. but that seems unlikely given the geometry that Burns documented. Another more compelling possibility is that 3I Atlas is not actively outgassing in the way we expect a comet to. If the object is mostly solid, if it does not have significant volatile ices on its surface, then a CME impact would not trigger enhanced sublimation because there would be nothing to sublimate. You cannot energize gas that is not there. A metal-rich body, a solid chunk of carbon and nickel alloy, as Stephen Burns suggests, would shrug off a CME impact with minimal visible effects. The plasma would flow around it, the magnetic field would drape over it, but without a massive gaseous coma to interact with, there would be no dramatic brightening, no outburst, and no tail formation. This interpretation fits perfectly with the missing tail problem. It fits with the anomalous nickel without iron chemistry. It fits with the object's survival of perihelion without fragmentation. If 3I Atlas is fundamentally different from normal comets in its structure and composition, then its response to solar heating and CME impacts would also be profoundly different. Normal comets are fragile, icy bodies that react violently to the sun's energy. 3I Atlas is not reacting the way normal comets do. That tells us something fundamental about what it is made of, about how it is constructed, and it forces us to question whether it is truly a natural object or something else entirely. The Punch satellite constellation, a set of spacecraft designed to image the region immediately around the Sun, observe 3I Atlas at perihelion. The processed images show a compact source, not something dramatically different from pre-perihelion observations, despite the object being at its hottest and most stressed moment. The JWST spacecraft began its observations on November 2nd, just days after perihelion and after the CME impact. JWST is in a unique position to see the object from the side, at a time when its activity should have been at its maximum. However, we will not see that data until February, when the spacecraft has sufficient bandwidth to transmit its observations back to Earth. That agonizing delay means we have to wait for what could be the most crucial evidence of all. The pattern that is emerging is remarkably consistent. Extreme solar heating does not produce the expected effects. A direct CME impact does not trigger an outburst. The passage through perihelion does not lead to fragmentation or dramatic tail development. Every single prediction based on the natural comet model fails to match the observations, and every one of those failures is another data point suggesting that 3I Atlas is not what we thought it was. The solar storm should have done something spectacular. The fact that it did nothing at all is becoming as loud a signal as any positive detection could be. Avi Loeb, in an effort to bring some quantitative rigor to the study of interstellar objects, created a ranking system. It is a scale from 0 to 10 that quantifies how likely an object is to be artificial rather than natural. A score of 0 means the object is definitely natural, something we can understand completely through conventional astrophysics. A score of 10 means it is definitely technological, with unambiguous evidence of design and manufacture. Most objects, like asteroids and regular comets, score a 0. The previous interstellar comet, 2I Borisov, scored a 1. It was overwhelmingly consistent with being a natural object. The first interstellar object ever detected, Oumuamua, scored much higher, around a 6 or 7. Its extreme shape, its tumbling motion, and its acceleration without any visible outgassing pushed it high up the scale, into a territory where natural and artificial explanations compete on roughly equal footing. 3I Atlas currently ranks at a 4 on the Loeb scale. That places it squarely in the middle ground. More anomalous than 2I Borisov, less mysterious than Oumuamua, but definitely strange enough to warrant serious investigation far beyond casual observation. A ranking of 4 means we can no longer dismiss the artificial hypothesis without addressing specific observations that do not fit our natural models. This ranking is not based on a single feature, but on the cumulative weight of 10 documented anomalies, each with its own low probability of occurring naturally. Let me walk you through them, because it is the pattern of multiple unusual characteristics appearing together in one object that is so compelling. Anomaly 1 is the trajectory alignment. 3I Atlas follows a retrograde orbit that is aligned to within 5 degrees of the ecliptic plane, the flat disk where all the major planets in our solar system orbit. For an object arriving from a random direction in the galaxy, the probability of being this closely aligned by pure chance is about 1 in 500. Anomaly 2 is the sunward jet. During July and August, 3I Atlas displayed an anti-tail, a jet of material pointing toward the sun, not away from it. This was not an optical illusion. It was a real stream of material, a phenomenon incredibly difficult to explain with standard cometary physics, especially when the object was still so far from the Sun. Anomaly 3 is its mass and speed. The nucleus of 3I Atlas is roughly 1,000,000 times more massive than Oumuamua, and it is moving faster through the galaxy than either of the two previous interstellar objects. The probability of us detecting an object this large and this far so early in our search for interstellar visitors is less than 0.1%. Our surveys are biased to find smaller, slower objects first. Anomaly 4 is the arrival timing and geometry. 3I Atlas achieved close passes to Mars, Venus and Jupiter, all while being conveniently unobservable from Earth during its critical perihelion period. The probability of an object on a random interstellar trajectory achieving this specific complex geometry is about 1 in 20,000. Anomaly 5 is the anomalous chemistry. As we discussed, the gas plume contains nickel without a corresponding amount of iron, and the nickel to cyanide ratio is orders of magnitude higher than in any known comet. The probability of this chemistry occurring naturally is estimated to be below 1%. Anomaly 6 is the low water content. 3I Atlas contains only about 4% water, far lower than typical comets. This suggests it either formed in an extremely cold environment, or that some process preferentially depleted its water, both of which are unusual. Anomaly 7 is the extreme negative polarization. The light reflecting off 3I Atlas exhibits polarization properties that have never before been seen in any comet. This indicates that the dust grains, composition or structure of the object are unlike anything we have ever studied. Anomaly 8 is the brightening and blue colour. Near perihelion, 3I Atlas brightened and shifted its colour toward blue wavelengths. This is unexpected for a cold, dusty object, which should scatter red light more efficiently and appear reddish. Anomaly 9 is the acceleration without a corresponding gas cloud. This is the core 13% problem. The measured acceleration requires a massive amount of mass loss, but our observations show no evidence of the enormous gas cloud or tail that this mass loss should have produced. Anomaly 10 is the lack of a tail post-perihelion. This is a summary of its incredible resilience. It survived extreme solar heating and a direct impact from a coronal mass ejection without producing the spectacular tail that all of those energetic processes should have created. Now, here is the critical point about the Loeb scale and these 10 anomalies. It is not about any single anomaly being impossible to explain naturally. You can probably construct a convoluted natural explanation for almost any one of them in isolation. The problem is explaining all 10 of them simultaneously with a single coherent natural model. At some point, the accumulated unlikelihood of the natural explanation may be surpassed by the simpler, if extraordinary, artificial explanation. This is the principle of Occam's razor. A ranking of 4 is not a conclusion. It is an assessment of where we are based on the current data. As more observations come in, that ranking could move. If the December observations show a massive gas cloud, the ranking will drop. If they confirm the absence of a gas cloud, the ranking will climb, possibly into the territory where the artificial hypothesis becomes the more likely explanation. The scale is dynamic, forcing us to continuously evaluate what the data is telling us, rather than locking into a position based on our prior assumptions. 3I Atlas currently sits suspended in that uncomfortable space where neither explanation is fully satisfying, where the data pushes us away from conventional interpretations, but does not yet give us enough to fully embrace unconventional ones. On December 19th, 3I Atlas will make its closest approach to Earth, coming within 269 million kilometers. By cosmic standards, that is remarkably close for an interstellar object, close enough for our most powerful telescopes to achieve unprecedented resolution and sensitivity. That date, December 19th, will either resolve this profound mystery or deepen it beyond anything we have seen so far. Every major observatory on the planet will be pointed at 3I Atlas that week. This will be a full-court press, the astronomical equivalent of throwing every resource we have at a single target. The observations from the James Webb Space Telescope are the most critical. Its near-infrared spectrograph can measure the composition of the Coma with exquisite precision. It will tell us exactly what is in that gas cloud and how much of it there is. The data from Webb will not be ambiguous. It will not leave room for hand-waving or appeals to uncertainty. We will know. The key question Webb will answer is whether the mass of the gas surrounding 3I Atlas is consistent with that 13% mass loss required by its acceleration. If Webb measures the gas mass and finds billions of tons of material present, the natural comet hypothesis survives. If Webb finds orders of magnitude less gas, the hypothesis fails. It is a simple, binary outcome. The gas is there, or it is not. There is a possibility that makes many people uncomfortable, but it must be considered. What if Webb finds almost no gas? What if the coma it detects is similar to the modest one we saw back in August, with no evidence of massive recent outgassing? At that point, we would have a fundamental, undeniable contradiction in the data. The acceleration requires mass loss. The mass loss must produce a detectable gas cloud, but the gas cloud is not there. Something in that chain of reasoning must be wrong, and the most likely candidate would be the assumption that the acceleration was caused by natural sublimation. December 19th is also crucial for studying the object's rotation. Natural comets are usually in a state of chaotic rotation, tumbling end over end. If 3I Atlas shows stable rotation around a single axis, that would be highly unusual for a natural object, but would be perfectly expected for a designed artifact like a spacecraft. We will also be searching for any radio emissions. SETI organizations have been monitoring 3I Atlas since its discovery, and this close approach is our best chance to detect any artificial signals before the object moves too far away. The most likely outcome is that the December observations will either confirm or refute the natural comet hypothesis based on the mass of the gas cloud. That single measurement is the linchpin. Everything else, the rotation, the polarization, the radio searches, will provide supporting evidence. Loeb has stated repeatedly that he will accept whatever the data shows. This is the scientific method in action. You propose hypotheses, you test them, and you update your beliefs based on the evidence. Ego has no place in this process. Only the data matters. The window for these critical observations will last for about 6 weeks. In that time, we will gather more data on this object than we have for any previous interstellar visitor. We will push our instruments to their absolute limits, and we will answer the questions that have been accumulating since a telescope in Chile first spotted an object that would challenge everything we thought we knew about comets, about interstellar visitors, and perhaps about our very place in the universe. December 19th is the date, the final test, the moment of truth. Let's talk directly about the hypothesis that we have been circling for this entire investigation. The idea that 3I Atlas might be using a propulsion system, that its acceleration is not due to natural outgassing, but to directed thrust from some form of engine. This is not speculation for entertainment value. This is a scientific hypothesis based on a growing list of observations that do not fit natural explanations. It makes testable predictions, it can be falsified, and whether we like it or not, it is becoming increasingly difficult to dismiss. The basic logic is straightforward. We observe non-gravitational acceleration. The natural explanation for this, the rocket effect from sublimated gas, requires a massive, visible gas cloud that we do not observe. If natural sublimation cannot explain the acceleration, we need an alternative mechanism. A propulsion system elegantly explains both the acceleration and the absence of a massive tail. Technological propulsion systems can achieve much higher exhaust velocities than natural sublimation, requiring far less mass to be expelled to produce the same amount of thrust. Adam Hibbard, a colleague of Loeb, pointed out something fascinating about the timeline of the object's behavior. 3I Atlas displayed that strange sunward jet, the anti-tail, during July and August when it was still far from the sun. Then, as it approached perihelion, that anti-tail diminished. Hibbard noted that if 3I Atlas were a spacecraft slowing down using forward-facing thrusters, this is exactly the behavior you would expect. The anti-tail could be evidence of a braking maneuver, a controlled deceleration to fine-tune its trajectory for close passes of the planets in our solar system. This interpretation seems far-fetched until you look again at the arrival geometry. The probability that a random interstellar trajectory would bring an object this close to Mars, Venus, and Jupiter, all while being hidden from Earth during perihelion, is about 1 in 20,000. When you multiply that by the 1 in 500 probability of its ecliptic alignment, the odds of the trajectory happening by chance drop to around 1 in 10 million. At that point, the trajectory itself starts to look less like a coincidence and more like evidence of intentional targeting. If you wanted to design an interstellar mission to survey our solar system, this is exactly how you would do it. You would aim for the ecliptic plane where the planets are. You would time your arrival for multiple planetary flybys. You would use the sun for a gravity assist. And you might do all of this while minimizing your visibility from the most technologically advanced planet, Earth, to avoid detection. The mission profile that makes perfect sense for an intelligent probe happens to perfectly match what 3I Atlas actually did. The anomalous nickel chemistry also fits this hypothesis. If 3I Atlas were a manufactured probe built to survive for millions of years in interstellar space, nickel-based alloys would be an excellent construction material due to their strength and durability. Detecting nickel without iron could be evidence of these advanced materials being shed from its surface. The on and off nature of the acceleration also fits. It behaved like an inert object for months, then the acceleration suddenly appeared near perihelion. This is exactly what you would expect from a propulsion system activating for specific maneuvers and then shutting down. Natural sublimation, by contrast, should follow a smooth, gradual curve of activity. If 3I Atlas is a probe, where is it from? How long has it been travelling? We do not know. At its incredible speed, it would take tens of thousands of years to cross even relatively short interstellar distances. An object built to function after 100,000 years of travel would need to be incredibly robust, likely a dormant artifact for the vast majority of its journey, activating only when it approaches a star system of interest. The anti-tail, the acceleration, the blue glow, these could all be signs of this reactivation. Why has it not communicated with us? There are many possible reasons. It might not be designed to. It might be communicating in ways we cannot detect. It might be malfunctioning. Or, and this is a profound possibility to consider, it might be deliberately avoiding communication. An advanced civilization might program its probes to observe emerging civilizations like ours without interfering, following a non-contact directive. A probe following that rule would look exactly as 3I Atlas appears to look. This propulsion system hypothesis is also falsifiable, which is crucial for its scientific credibility. If the December observations from the Webb telescope show the massive gas cloud required by natural sublimation, then this hypothesis is wrong. If the data supports the natural explanation, we must accept it. But if the gas cloud is not there, if the anomalies remain, then we must take the alternative seriously, regardless of how uncomfortable it makes us. The discomfort is understandable. Accepting that 3I Atlas might be a probe means accepting that we are not alone, that other civilizations exist with technology capable of interstellar travel, and that one of their artifacts is currently passing through our solar system. Those are enormous implications, but discomfort is not a reason to reject a hypothesis if it is where the evidence leads. Over the next few months, the data will come in. We do not have to speculate endlessly. By the spring of next year, we will know far more about what 3I Atlas actually is. Until then, the propulsion system hypothesis remains on the table, neither proven nor disproven, but increasingly difficult to ignore. What happens if we are wrong? There are two ways we could be wrong about 3I Atlas, and the implications of each are profound. We could be wrong in thinking it is a natural object when it is actually technological, or we could be wrong in suspecting it might be technological when it is actually just an exotic but natural object. Both errors carry serious consequences for how we approach the search for life in the universe. Let's start with the first, and perhaps most tragic scenario. Suppose 3I Atlas is indeed a probe, an artifact from another civilization, and we fail to recognize it as such. Suppose we dismiss the anomalies, we explain them away, and we let this object pass through our solar system and leave without us ever confirming what it actually was. What have we lost? We have lost a once-in-a-civilization opportunity to study extraterrestrial technology up close. 3I Atlas is here now. It is accessible. We could potentially send a mission to intercept it, but that opportunity exists for a very limited time. But the loss goes far beyond just this one object. If we fail here, we establish a pattern of dismissing evidence because it does not fit our comfortable narratives. 3I Atlas will not be the last interstellar object we detect. Our survey capabilities are improving dramatically. More will come. If we develop a habit of explaining away anomalies rather than investigating them rigorously, we risk missing first contact not because the evidence was not there, but because we refuse to look at it honestly. Now consider the second scenario. Suppose 3i Atlas is natural, and we invest significant resources investigating it under the assumption that it might be technological. Suppose the December observations resolve all the mysteries and confirm it is just a weird comet. What have we lost in that case? Honestly, not much. We would have conducted a thorough, multi-wavelength observational campaign on an interstellar object, gathering priceless data that advances our understanding of comets and the formation of star systems. Even if the technological hypothesis is wrong, the science we do to test it is incredibly valuable. The asymmetry here is striking. If we treat 3i Atlas as possibly technological and we are right, we make the single greatest discovery in human history. If we treat it as possibly technological and we are wrong, we still do excellent science. But if we assume it is natural and we are wrong about that, we lose a historic opportunity that may not come again in our lifetimes. The risk-reward calculation overwhelmingly favours investigation. This is a version of Pascal's wager applied to astrobiology. The potential payoff for being right is so immense that it justifies the modest cost of investigation, even if the probability of success is low. There is a deeper philosophical point here. For centuries we have been learning that humanity is not special, that we are not the centre of the universe. Yet, in one area, we still cling to the assumption that we are unique. We assume we are alone. This assumption has no empirical basis. 3i Atlas challenges this final bastion of human exceptionalism. It forces us to move the search for extraterrestrial intelligence from the realm of abstract radio searches into the practical observational study of physical artifacts. Maybe we have been looking for evidence in the wrong place. Maybe first contact will not come through a message beamed across light years, but through an artifact that visits us. An artifact that can be photographed, studied, and perhaps one day even touched. Maybe that artifact is already here, has been here since July, and is preparing to leave in just a few months, unless we act decisively to study it more thoroughly. What happens if we are wrong? If we underestimate 3i Atlas, we may miss our moment in history. If we overestimate it, we do good science and remain humble about the limits of our knowledge. The asymmetry is clear. The choice should be obvious. The data is coming, and very soon we will know whether we live in a universe where we are alone, or a universe where others have visited, observed, and moved on, while we were still arguing about whether the visit actually happened. The choice should be obvious, but in the real world of science, it rarely is. The history of discovery is filled with moments where the data pointed toward a revolutionary new idea, but the scientific establishment, comfortable in its existing paradigms, resisted. Galileo was placed under house arrest for suggesting the Earth revolved around the Sun. Alfred Wegener was ridiculed for his theory of continental drift. The idea that meteorites were rocks that fell from the sky was once considered absurd. In each case, the evidence was there, but the intellectual and institutional inertia was too great to overcome without a prolonged, often bitter, fight. We are at such a moment right now with 3i Atlas. The easy path, the safe path for a scientist's career, is to assume it is natural. You can publish papers proposing exotic but natural explanations for each anomaly. You will get peer-reviewed, you will get funding, and you will not be labelled as a fringe thinker. The difficult path, the one Avi Loeb has chosen, is to follow the data wherever it leads, even if it leads to a conclusion that challenges our most fundamental assumptions. This path invites skepticism, professional risk, and sometimes outright ridicule. Why is this? Why is there such a powerful resistance to even considering the possibility of extraterrestrial technology? Part of it is a healthy scientific skepticism. Extraordinary claims do require extraordinary evidence. But part of it, I believe, is something deeper. It is a kind of psychological defense mechanism. The confirmation that we are not alone in the universe would not just be a scientific discovery, it would be a cultural, philosophical, and religious event of unparalleled magnitude. It would force a re-evaluation of humanity's place in the cosmos. It would be destabilizing. For some, the implications are so profound that it is psychologically easier to find any reason, no matter how convoluted, to dismiss the evidence rather than confront what it might mean. This is the human drama playing out behind the scenes of the scientific investigation. It is a conflict between caution and curiosity, between protecting the established order and venturing into the unknown. The silence from many mainstream institutions is not necessarily a sign of a conspiracy. it is more likely a sign of deep-seated institutional caution. No one wants to be the NASA administrator or the university professor who cries aliens only to be proven wrong by a mundane explanation a few months later. The professional embarrassment would be immense, but as we have already discussed, the cost of being wrong in the other direction, of crying Comet when an alien probe is sailing past your window, is infinitely greater. This is why the data from December 19th is so absolutely critical. It has the power to cut through the debate, the caution, and the fear. The James Webb Space Telescope does not have a career to protect. It does not have philosophical biases. It is a machine for gathering light and turning it into data. It will measure the gas cloud, or the lack thereof, with cold, impartial precision, and at that point the debate will be forced to shift from what we believe to what we know. The data will either provide a safe harbour for the natural explanation, or it will push us out into the deep, uncharted waters of the technological one. Let's venture into those waters for a moment. Let's assume, for the sake of argument, that the December observations confirm our worst fears. The acceleration is real, but the massive gas cloud is not there. What kind of propulsion system could actually achieve this? What technology are we talking about? This is not just science fiction, it is a question of applied physics. The most straightforward technological explanation would be a form of electric propulsion, like an ion drive. An ion drive works by using electricity, likely from a nuclear power source or advanced solar panels, to ionize a gas like xenon or argon. It then uses powerful electric or magnetic fields to accelerate these ions to extremely high speeds and shoot them out the back of the spacecraft. Because the exhaust velocity of these ions is incredibly high, tens of thousands of meters per second compared to the 300 meters per second of natural sublimation, you need to expel far, far less mass to get the same amount of thrust. An ion drive would perfectly explain the core mystery of 3I Atlas. It would produce the measured non-gravitational acceleration, but the amount of propellant it would need to expel would be so small that it would be completely invisible to our telescopes. It would be a ghost propulsion system, its effects visible only in the object's trajectory, not in a brilliant cometary tail. Modern ion drives on our own spacecraft are very low thrust, designed for gradual acceleration over long periods. But a civilization capable of interstellar travel would likely have developed far more powerful versions. An advanced ion drive could easily account for the subtle but significant course correction we observed in 3I Atlas as it passed the Sun. Another possibility is a solar sail. A solar sail is an enormous, ultra-thin mirror that reflects sunlight. The photons of light from the Sun, while massless, carry momentum. When they bounce off the sail, they transfer a tiny bit of that momentum, creating a gentle but continuous push. A large enough solar sail could produce a measurable acceleration, and it would do so without expelling any mass at all. The acceleration would be purely radial, directly away from the Sun, which matches one of the components of 3I Atlas's acceleration. However, the solar sail hypothesis has a problem. 3I Atlas also showed a transverse component of acceleration, a push sideways to the Sun's direction. A simple, flat solar sail cannot produce this kind of thrust. You would need to be able to actively change the shape or angle of the sail, or perhaps use reflective vanes to direct the thrust. Furthermore, we have not seen any direct evidence of a large reflective sail structure around 3I Atlas. While it is an elegant concept, it does not perfectly fit all the observations. The strange brightening and blue colour shift near perihelion, however, could be interpreted as evidence of some kind of light manipulating surface, but this is highly speculative. Then we move into more advanced, more speculative forms of propulsion. A fusion rocket, for example, would use the energy from nuclear fusion, the same process that powers the Sun, to heat a propellant to incredible temperatures and expel it at enormous speeds. A fusion rocket would be thousands of times more efficient than a chemical rocket, and could produce significant thrust. The exhaust would be a plume of superheated plasma, which might be detectable, but depending on its composition and density, it could still be much harder to see than a dusty cometary tail. The most exotic possibility, one that exists on the very edge of theoretical physics, is that 3I Atlas is not using a rocket at all. Some physicists have proposed that an extremely advanced civilization might learn how to manipulate space-time itself, creating a kind of warp drive that moves a bubble of space, with the craft inside it, from one point to another. This is for now purely theoretical. but if such a technology were possible, it could explain any kind of acceleration without any visible exhaust whatsoever. We do not need to resort to such exotic explanations yet. A powerful ion drive or a similar electric propulsion system, a technology we are already using in its infancy, is sufficient to explain the primary anomaly of acceleration without a tail. The fact that a plausible, known technological solution exists makes the artificial hypothesis that much more compelling. We're not invoking magic, we're invoking an advanced application of physics we already understand. The nickel without iron chemistry could be explained by the use of advanced alloys in the construction of the probe and its engine. The on and off nature of the acceleration could be the engine firing for a specific course correction and then shutting down to conserve energy. The pieces fit together into a coherent, self-consistent picture. This brings us back to Oumuamua. For a long time, Oumuamua was a solitary data point, a one-off mystery. It was easy for critics to dismiss its anomalies as a fluke, a measurement error, or the result of it being a completely new type of natural object we had never seen before, like a nitrogen iceberg. But now we have 3I Atlas, and while the two objects are very different in size and composition, they share the single most important anomaly: non-gravitational acceleration without a visible cometary tail. This is no longer a single, isolated event. We now have a pattern. Two of the first 3 interstellar objects ever detected in our solar system have exhibited this specific, highly unusual characteristic. The odds of this happening by chance, if these objects are drawn from a random population of natural comets and asteroids, are vanishingly small. It suggests that objects with this particular anomalous property might be common in the interstellar medium. So what does this pattern mean? One possibility is that there is a class of natural interstellar objects that behave this way, and we simply do not have a theory for them yet. Perhaps they are hydrogen icebergs, as some have proposed, which would produce an invisible exhaust of hydrogen gas. Or perhaps they are something even stranger. Science is always open to the discovery of new natural phenomena, but there is another, more tantalizing possibility. What if we are not seeing a class of natural objects, but a class of technological ones? What if Oumuamua and 3I Atlas are related? Not necessarily from the same civilization, but perhaps examples of a common type of technology used for interstellar exploration. Probes designed to be stealthy, efficient, and resilient. Oumuamua, being much smaller and faster, could have been a scout, a flyby mission designed for rapid reconnaissance. 3I Atlas, being 1,000,000 times more massive and moving more slowly through our system, could be something different: an orbiter, a long-term observatory, or even a mothership carrying smaller probes. The trajectory of 3I Atlas, with its multiple planetary flybys, is much more consistent with a detailed survey mission than Oumuamua's simple hyperbolic path. It is almost as if Oumuamua was the first quick look, and 3I Atlas is the follow-up, sent to take a closer, more detailed survey. This is, of course, pure speculation, but it is speculation grounded in the pattern of evidence we are observing. When you have 2 data points that share the same inexplicable feature, you're no longer dealing with an anomaly, you're dealing with a category. And the defining characteristic of this new category of interstellar objects is that they behave as if they are propelled. This is why the stakes for the December observations are so high. They are not just about understanding 3I Atlas, they are about understanding the entire population of interstellar objects. If 3I Atlas is confirmed to be a natural comet, it casts Oumuamua in a new light, suggesting that its own anomalies might also have a natural, if exotic, explanation. But if 3I Atlas is confirmed to have no massive gas cloud, it strengthens the case for Oumuamua being artificial as well. It would suggest that our galaxy is populated with technological artifacts, and that they are passing through our solar system with a frequency we never imagined possible. Imagine the scene on December 19th. In control rooms around the world, from the Space Telescope Science Institute in Baltimore that operates Hubble and Webb, to the European Southern Observatory in the Atacama Desert that operates the VLT, teams of astronomers will be waiting. The observation schedules for these billion-dollar instruments are planned months, sometimes years, in advance. To get time on the James Webb Space Telescope is one of the most competitive pursuits in all of science. The fact that it will be pointed at 3I Atlas during this critical window tells you how seriously the astronomical community is taking this object, even if they are reluctant to discuss its most radical implications in public. The commands will be sent. The telescope, 1,000,000 miles from Earth, will pivot its golden mirrors. Its instruments, cooled to just a few degrees above absolute zero, will begin to collect the faint infrared light from 3I Atlas. For hours, photons that have travelled 269 million kilometres from the object will strike its detectors, building up a signal line by line. That data will be packaged and beamed back to Earth, where it will be processed, calibrated, and turned into a spectrum. And on that spectrum there will be an answer. It will show the chemical fingerprints of the molecules in the coma. It will reveal the presence of water, of carbon dioxide, of cyanide, and yes, of nickel. But most importantly, the strength of those signals will tell us the density of the gas. From that, we can calculate the total mass. It will be a number, and that number will either be in the billions of tons or it will not. There is no middle ground. The moment that first spectrum appears on a screen will be one of the most tense and significant in the history of astronomy. The scientists who see it first will know. They will know if the mystery is solved or if it has just begun. They will know if they are looking at the data from a weird comet, or if they are looking at the first confirmed, irrefutable evidence of a technology beyond our own. What happens in the hours and days after that? If the gas cloud is there, a press release will be issued. It will state that observations have confirmed the presence of a substantial coma consistent with the object's acceleration being caused by cometary outgassing. The mystery, it will say, is solved. 3I Atlas is a natural object. The news cycle will move on. But what if the gas cloud is not there? The silence will be deafening. There will be no immediate press release. The data will be checked, rechecked, and checked again. Every possible source of instrumental error will be investigated. Other telescopes will be tasked with confirming the observation. But if the result holds, if Webb, Hubble, and the VLT all agree that the gas required by the laws of physics is absent, then the world will change. At some point, an announcement will have to be made. It will be the most carefully worded, heavily scrutinized scientific statement in human history. It will not say, "We have found an alien spaceship." It will likely say something far more cautious. Observations of 3I Atlas have revealed a significant discrepancy between its observed acceleration and the mass of its gaseous coma. The data is inconsistent with all known models of natural cometary activity. The origin of the acceleration remains unknown. But everyone will know what that means. It will mean that the natural explanation has failed, and the only remaining hypothesis is the technological one. The news will not just be on science websites. It will be the leading headline on every news channel in every newspaper in every language on Earth. The political, social, and cultural impact would be immediate and overwhelming. Governments would have to respond. Would 3I Atlas be seen as a threat, a resource, an opportunity? The United Nations would convene. Military agencies would scramble to track the object with their most powerful radar systems. The demand for a mission to intercept 3I Atlas would become a global clamour, no longer the proposal of a single congresswoman but a planetary imperative. The public reaction would be a tidal wave of every human emotion: fear, wonder, excitement, denial, and a profound sense of awe. Our entire perspective on our own existence would shift. The question, "Are we alone?" would be answered, and the answer would be no. We would be forced to confront the reality that we are a young civilization in a very old and likely crowded galaxy. This is what is at stake on December 19th. This is the magnitude of the question that the James Webb Space Telescope is being asked to answer. We are standing at a crossroads. Down one path lies the familiar comfort of a universe that, while vast and mysterious, is ultimately understandable in natural terms. Down the other lies a universe that is not just mysterious, but inhabited. A universe in which we are not the only minds, not the only builders, not the only travellers. The data will decide which path we take, and in just a few short weeks that data will arrive. Until then, all we can do is watch, wait, and prepare ourselves for the possibility that our understanding of the universe is about to be changed forever. The tale that never came may be the quiet herald of the most transformative discovery in the history of our species. The silence from 3I Atlas may be the loudest message we have ever received. It is a message that tells us to look up, to question our assumptions, and to be ready for a cosmos far stranger and more wonderful than we have ever dared to imagine. And yet, as we stand on the precipice of this potential revelation, we must also prepare ourselves for a third possibility, one that is perhaps the most frustrating and the most human of all: ambiguity. The universe rarely provides the simple, binary answers we crave. We have framed the December 19th observation as a definitive test, a moment of truth where the gas cloud is either present or absent. But what if the James Webb Space Telescope delivers a result that lies somewhere in the murky middle? What if it detects some gas, but not nearly enough to account for the full 13% mass loss required by the acceleration? Imagine a scenario where the data shows that 3I Atlas shed, say, 3% of its mass. This would be a significant outgassing event, far more than a simple inert asteroid would produce. It would be enough for supporters of the natural explanation to claim victory, pointing to the presence of a coma as proof of cometary activity. Yet, it would still leave a massive unexplained acceleration. It would not solve the problem, it would only shrink it. We would be left with a hybrid object, a thing that is partially a comet, but also partially something else. The mystery would not be resolved, it would be redefined, becoming even more complex and harder to grasp. This grey area outcome would satisfy no one and inflame everyone. The debate would intensify, with one side arguing that our models for cometary, outgassing are simply incomplete, and the other side arguing that the remaining unexplained acceleration is the true signal of a low-power propulsion system operating in concert with natural processes. In this scenario, 3I Atlas would become a kind of cosmic Rorschach test, a canvas onto which we project our deepest beliefs and biases about the universe. The data would be a mirror reflecting our own willingness or unwillingness to entertain extraordinary possibilities. This outcome would also force us to confront a more subtle but profound question. If it is a probe that is also designed to look something like a comet, perhaps as a form of camouflage or to use natural resources for reaction mass, how could we ever tell the difference? A sufficiently advanced technology might be indistinguishable not from magic, but from nature itself. An engineered object could be designed to shed gas and dust, to create a coma that mimics a natural object, all while using a primary propulsion system for its main acceleration. In that case, the presence of some gas would not be evidence against technology, it could be a feature of it. The search for a simple, clean answer might be a fool's errand, a trap set by our own simplistic expectations of what an alien artifact should look like. This leads us to another fundamental question that has lingered in the background of this entire event. Why us? And why now? If 3I Atlas and Oumuamua are indeed technological artifacts, their arrival in our solar system within just a few years of each other is a coincidence of staggering proportions. Or perhaps it is not a coincidence at all. We must remember that we did not begin to see these objects because they just started arriving. We began to see them because we just started looking. The Pan-STARRS survey that discovered Oumuamua and the Atlas survey that discovered 3I Atlas are relatively new projects. They represent a new capability in our planetary defense and astronomical survey efforts, an ability to scan the entire sky rapidly and detect faint, fast-moving objects. We are seeing these interstellar visitors now because we finally built the wide-field eyes necessary to spot them. From this perspective, their arrival is not timed to our history, but to our technological capability. This raises a fascinating and slightly chilling possibility. For billions of years, our solar system may have been visited by such objects, passing through completely unnoticed by the pre-technological life on our planet. We were simply blind to them. Now that we can see, we're beginning to catalogue what has been passing by all along. This is the simplest explanation for the timing, but there is another, more speculative one. What if our own technological emergence is the trigger? The Fermi paradox asks, if the galaxy is filled with intelligent life, where is everybody? One proposed solution is the zoo hypothesis, which suggests that advanced civilizations are aware of us, but are deliberately hiding, observing us as if we are animals in a cosmic zoo, to allow our civilization to develop naturally without interference. What if our new sky surveys are the equivalent of the zoo animals suddenly developing binoculars and looking back at the observers? Our newfound ability to see them might change the rules of the game. Another related idea is that of a sentinel probe. An advanced civilization might seed the galaxy with millions of dormant probes, programmed to watch star systems for signs of emerging technology. For eons, a probe in or near our solar system would have seen nothing but a quiet, living planet. But then, In the last century, that planet began to glow in the radio spectrum. We invented radio, then television, then powerful radar systems for military and scientific use. Our planet is now a beacon of artificial radio waves, broadcasting our existence to anyone listening. Perhaps these signals, propagating out into space at the speed of light, finally reached a dormant probe. Its instructions might be simple. Upon detection of artificial signals, activate, approach the source system, and conduct a detailed survey. In this scenario, Oumuamua and 3i Atlas are not random visitors. They are a direct response to our own technological coming of age. They are here because we are here, and because we finally made enough noise to be noticed. This would mean that first contact is not something we are waiting for. It is a process that has already begun, initiated not by us, but by them, in response to us. While we await the verdict from the James Webb Space Telescope, we must not forget the other crucial pieces of evidence that are still to come. The European Space Agency's JWST spacecraft, on its long journey to Jupiter, had a unique opportunity that no Earth-based observatory could match. As it flew through the solar system, its trajectory brought it to a position where it could view 3i Atlas from the side, a completely different vantage point from our head-on view from Earth. These observations, which took place in early November, are currently stored in the spacecraft's onboard memory. Because of the spacecraft's distance and the limited bandwidth of its communication link, we will not receive that precious data until February 2024. The wait will be agonizing, but the payoff could be immense. JWST's submillimeter wave instrument, or SWAY, is specifically designed to detect water vapor. It will provide an independent, powerful measurement of the water content in the Coma, a critical piece of the chemical puzzle. More importantly, its Janus imaging camera will show us the morphology of the object from a 90-degree angle. From Earth, it is difficult to distinguish the shape of a coma from the shape of a tail that is pointing directly away from us. From the side, JWST will see the object in profile. It will see unambiguously whether there is a tail streaming out behind 3i Atlas. If Earth-based images show no tail and JWST's images show no tail from the side, it would be the final nail in the coffin for any explanation that relies on a hidden or difficult-to-see gas plume. The JWST data is our independent verification, our crucial second opinion that can either confirm or contradict what Webb tells us in December. There is also the tantalizing possibility of using radar. While the famous Arecibo Observatory is no longer operational, NASA's Goldstone Solar System radar in California has the power to send a powerful beam of radio waves out to 3i Atlas and detect the faint echo that bounces back. A radar observation would be a game changer. It would not just tell us about the gas cloud, it would tell us about the nucleus itself. The way radar waves reflect off a surface depends entirely on what that surface is made of. A porous, icy, dusty rubble pile, like a normal comet nucleus, would return a very weak, diffuse radar signal. However, a solid metallic surface would be an excellent radar reflector, returning a strong, sharp echo. A successful radar detection could, in a single observation, tell us if the core of 3i Atlas is a solid object, and whether it is rich in metals. It could even give us clues about its shape and rotation. If 3i Atlas returns a radar signature that indicates a smooth, metallic, rapidly rotating object, the debate would be over. That is simply not a combination of properties that occurs in nature. The challenge is the immense distance, but during the December 19th close approach, it might just be possible. Ultimately, the story of 3i Atlas is about more than just one strange object. It is about how science works at its best, and sometimes at its most frustrating. Science is not a collection of facts in a textbook. It is a process of inquiry, a method for confronting the unknown. An anomaly like 3i Atlas is the greatest gift the universe can give to science. It is a puzzle that stretches our theories to their breaking point. It forces us to question our assumptions, to build better instruments, and to imagine possibilities we had never considered. Regardless of whether 3i Atlas turns out to be a comet, a probe, or something in between that we do not even have a name for yet, the process of studying it will leave us richer. We will have pushed our telescopes to their absolute limits. We will have developed new ways to analyze data. We will have engaged in a global conversation about our place in the cosmos. And we will have been reminded that the universe is under no obligation to conform to our expectations. The final chapter of this story has not yet been written. It will be written in the data that flows back from our robotic emissaries in the cold darkness of space. It will be written in the debates and discussions that take place in university halls and online forums. And it will be written in the hearts and minds of every person who looks up at the night sky and wonders, with a newfound sense of urgency and awe, if we are truly alone. The journey of 3i Atlas through our solar system is a fleeting moment in cosmic time, but its journey through our collective consciousness is just beginning, and it is a journey that promises to change us forever. This change is not something that will be handed down to us from a scientific authority. It is a change that happens within each of us, every time we choose curiosity over certainty. This investigation is not a spectator sport. It is an invitation for you, for me, for all of us, to participate in the greatest detective story ever told. You can follow the data releases from NASA and the ESA. You can join online forums where amateur astronomers are sharing their own observations and analysis. You can read the papers, listen to the debates, and form your own conclusions based on the evidence. The most profound discoveries are not those that are simply told to us, but those that we come to understand for ourselves. So as we wait for the photons from 3i Atlas to complete their long journey to the mirrors of the Webb telescope, I ask you to consider this. What would it mean to you, personally, if we found out we are not alone? How would it change the way you see the world, your place in it, and the future of our own species? Perhaps the ultimate message of 3i Atlas is not written in its trajectory or its chemistry, but in the questions it forces us to ask about ourselves. It holds up a mirror to our hopes, our fears, and our own aspirations to one day reach for the stars. The journey of 3i Atlas may be temporary, but the journey it has ignited within us has only just begun.